All right. Thank you again, guys, for joining us. We are here for our Tech Tuesday. I just want to take just a couple minutes to take care of a couple, really just tabletop conversations about things that we need to just make sure of that happens throughout our process of meetings with the association. First things first is our CRMCA Tech Tuesday, and for any of our meetings, the antitrust. The information is up on the screen for you guys to read, but this is just basically an understanding that we are not here to talk about monies, costs of things, comparisons of any sort, including company comparisons or direct conversations about specific products. Urs is here to talk about hot weather concrete, and in general, he will not be talking about any specific products. And then for any of you guys that may not be a CRMCA member, we do have memberships available for companies. So if you're working for a specific company, check with your administration to find out if they are members of the association. There are many different benefits. I always like to point out the ACI certification benefit. It's always about 40% discount here in Colorado. But there are many other benefits to the membership, including governmental affairs conversations and several different committees that we run throughout the state. So if you have questions, do reach out or go to our website for more information. So with that, thank you again. This is our CRMCA Tech Tuesday. It is, what is it, May 14th of 2024. So thank you guys all for joining us. Before I get started, I do want to make sure that if you guys have any questions for those that are on Zoom or in the other watch parties on the Western Slope or up in Denver, please do message them in the message chat or the meeting chat. And if I can answer them, as I'll be controlling that, I will. If not, we will answer any major questions with hers at the end of the presentation, but do not hesitate to post those questions as we are rolling through. Also, please do make sure you're on mute. I'd ask that nobody does try to interrupt through voice. This is more of a presentation mode than anything else, but so utilize that chat to the fullest. And then also thank you guys for to the sponsors, both Wholesome and GCC are sponsoring this event today for hot weather concrete. For future events, we will have the registrations available for next month's session and for flatwork finishing in June. Sponsorships are available for those as well once that registration is open. So with that, I will pass it over to Urs Fox and I'll allow him to introduce himself, and we'll have him talk about hot weather concrete.
Thanks, JT. Good afternoon, everybody. So today's topic is hot weather concrete. Most 80% of my presentation is really based on the design and control of concrete mixtures. It's quite a book from a PCA, but it has a lot of really valuable information. If you don't have it, I would highly recommend that book to anybody of you, just for general information. Let me see whether that clicker works. Here we go. Just one thing first, type 1L, Portland limestone cement. We know, everybody, it's out there. We know that certain issues have arisen or may have arisen. There will be a future Tech Tuesday, that's going to be in July, about PLC. We know there are maybe some performance differences between the OPCs and the PLCs. Also differences between PLCs from different cement suppliers. Our recommendation, like for any change in material, is perform your mix design and perform field testing if at all possible. So a test placement is always valuable just to see how the concrete finishes, the workability, just the whole placement, how it works. So again, 1L, there might be a little bit more sensitive, but the topic today is really about general hot weather concreting. Impacts of hot weather on concrete properties. Generally, optimum concrete temperature is around 50-60 F. We all know that more realistic temperatures are between 50 and 90 F, sometimes even higher. Hot concrete has adverse effects. Heat of hydration, it accelerates faster. Evaporation of water and faster set. So everything goes a little bit quicker if we have hot concrete or if we have hot weather out there. Check. Detrimental hot weather conditions that may include high air temperature. We all know can hit easily 100 degrees in the months of July and August. High concrete temperature, low relative humidity. We've seen, or we see quite often, humidity is down in the single digits, below 20%, below 10%. High wind speed and solar radiation. So if we talk about hot weather conditions, these are all the conditions that we include for this topic. Problems that may be created by hot weather or hot concrete, increased water demand, accelerated slump loss. So you batch at the plant, you drive out 45 minutes, 60 minutes, you might have quite some slump loss, especially at hot temperatures. It's more difficult to control the air in hot concrete. Set times are much faster. Plastic shrinkage, cracking, and crazing, that is increased generally if you have hot weather conditions. You have more potential for shrinkage. Thermal cracking might be an issue. And what we see quite often is that you have pretty good, pretty nice early strength in the concrete, but later you will see that the 28 days don't make it that high. So accelerate in the beginning, but it tables off really fast if you have hot weather, hot concrete. Let's talk about workability, slump loss. Slump loss is often compensated with water addition, resulting in lower strength. So here's an example. So I go through that chart. What we see up there is if we take a temperature of around 50 Fahrenheit, we go down the graph, we see that we need, in this example, around 270 pounds water per yard of concrete. If we go from 50 to 100 degrees, given this is an extreme example, but if we go to 100 degrees, we now need an additional 33 pounds of water. That is about 4 gallons per yard additional to maintain the same slump. So that means in the end, per 10, 15 degrees increase, we need about 1 to 2 gallons more of water. If we actually add water, we're going to reduce the strength quite a bit. So the general rule of thumb is you add 1 gallon of water per yard, you're going to lose 200 to 300 psi. In this example, which is extreme, we would lose about 20% or roughly 1,000 psi at 28 days for that concrete. So always the recommendation is easier said than done, especially when you get to the construction site, is add hydration stabilizer or water reducer, don't add water. The water always will reduce your strength. So that's just a recommendation for the ready mix producers that they actually add any water addition to their tickets. Sometimes it's actually automatically done by their batch system, just to make sure that we have all the facts when should we have an issue later on. Again, slump loss, that is just because of the temperature difference. It's quite a bit, so we have to be careful that we don't add water, or at least not too much water at the construction site. We dilute the concrete and we reduce the strength. There's a picture about calorimetry. So what we can do in the cement concrete lab, we can analyze the heat that is generated from the hydration process. We see in the upper curve, the cumulative heat that is generated over this here is 70 hours, so that's over 3 days. So you see the heat that is generated at 57, 68, 90. These were just the temperatures that we had in our lab. Couldn't get any lower in our lab. But you see there's quite a bit less heat generated at 57 compared to 90 F. And the heat of hydration from the calorimetry, it directly correlates with the strength development of cement. And we see in the lower graph, the power curve, I just shows a differential that shows that the highest heat generation in this case is around, I cannot see, it's about 7 hours for the 90 degree, and it's about 14 hours for the 57 Fahrenheit concrete. So again, the heat of hydration directly correlates with the strength development, and for us, it's a nice measure to see how a concrete, how a cement reacts different temperatures. And also we can do that with admixtures to see admixture compatibility with different concretes. Water content versus shrinkage. In this case, we see at the top from 210 to 460 pounds per yard water, and the drying shrinkage, how it increases. So in this case, that's a pretty old graph also from the PCA booklet. Was a large number of different mixtures, different proportions were done, and they show the shrinkage of the concrete. And what we see in the end is that the more water we have in our concrete, the higher the shrinkage of the concrete. So it's always good. Again, don't add any more water at the construction site. If you don't have to, the shrinkage might increase. Setting time, that's quite a busy graph, I know, but what we see is we have a concrete A, which is the blue concrete that shows the initial and the final set at different temperatures, 50, 73, and 90 degrees. And we see how the temperature, how the temperature increases, the set time decreases. Concrete B, which is a different concrete, just two different mixes. And we see there's quite a big difference between the set times. General rule of thumb is for every 20 F difference, you double the reaction time. This is basic chemistry, and it also works here for the set times. So let's say if you have an initial set of 4 hours at 70, the initial set will be 2 hours at 90 degrees. So you see there's that window for the finishability really shrinks a lot. That's something we need to consider. If we go from 70 to 50, then very likely the initial set will be around 8 hours.
So is there a direct correlation for smaller integrals of that temperature range? So if there's only a 5% difference, do you reduce that to?
Yes, yeah, you kind of can go by the graph generally, just so to go in between this. Yeah, you can interpolate these numbers, yes. Strength development at different temperatures. So we see here, first of all, it's a logarithmic scale, goes from 1 to 28 days and then to 365 to 1 year. What they did in this experiment is they cured the concrete at 73, 90, 105, and 120, which is extreme, I understand, F for 28 days. And then they put the cylinders in a moist cured room at 73 F. So, and what we see is that the 120 F, it takes off quite a bit. This is in megapascal. So that's about 40, that's about 6,000 PSI. You see the blue line, the dark blue line, around 38 takes off at the beginning one day, but it tampers off, it tables off. And then what we see is the one at 73F, it's at 20 MPa, around 3,000 PSI at one day, but it keeps developing, and it actually overtakes already at 28 days, the other ones, and then it stays on top. So again, what I mentioned at the very beginning, optimum concrete temperature 50 to 60 degrees. This is mainly because we really get the higher 28-day, the higher late strength. What we see in this case, if we go from 70 to about 100 F, we reduce the strength by 10 to 15 degrees. This goes actually also back, this is about concrete, just that's placed, but that goes back to what JT and Mike talked about a month ago, curing of cylinders. If you cure your cylinders out in the sun at 100 degrees, don't expect good 28-day strength. It's going to be low. They need to be cured at the defined temperature range. Help me out, JT, 68 to 80?
60 to 80 degrees
60,
for standard.
60
yes.
to 80 for standard, and then the window narrows if you go above 6,000 PSI.
Correct.
Yes. So again, if we have lower temperature of concrete, we will very likely get higher late stage strength of the concrete. This graph shows SCM, supplementary cementitious materials. Upper left is just a pure Portland cement. They were cured at 4673 and a 104. And you see that the one at 104 takes off very nicely and then tampers off again. I'm not sure why they put in there the H in hours, but that's like 700 hours. It's more or less 28-day strength. But you see that the 146.73, they gain momentum later on, and they keep on going. What we see is with slag, an F ash or a C ash, they help compensate because they slow down the hydration process in the very beginning, and they do this so that they help mitigate lower strengths later on. So again, SCMs are beneficial if we go for higher, if we have higher temperatures in concrete. Plastic, oops, that was one.
I clicked on it on my side, sorry.
Plastic shrinkage, cracking, and crazing. Generally, hot weather, hot concrete, it will increase the tendency for cracks in fresh and in hardened concrete. In fresh concrete, it's generally because of the rapid evaporation of the water that leads to plastic shrinkage, cracking. Hardened concrete, it's just a drying shrinkage, especially when we have higher water content. What we showed before, you have higher shrinkage and there are cracks that might develop. So in this case, you see the crazing cracks because of the rapid evaporation, and then a large dry shrink crack that just formed later on in the concrete. Reasons, again, for this kind of repetition for shrinkage, cracking, and crazing: low relative humidity, so if it's dry, like we have here in Colorado, increased wind speed in the afternoon, increased concrete temperature. the higher the cementitious material content, the higher the potential for cracking and crazing. Even though we like to sell cement as cement producer, we still recommend to lower the cement content generally in concrete to reduce the shrinkage cracking. Lower water cement ratio tend to go for higher drying shrinkage cracking crazing. Concrete mixtures with low bleed rates, silica fume mixtures, some of the new ternary blends that are coming out, they have really low bleed rates, and we have to be very careful about shrinkage cracking. I'm going to mention that later on when we go through some graphs about when we need to cure and when we may avoid the curing. Generally, one of the things we see is that finishers start finishing too early because the surface is drying out and they think that the concrete is ready to go on, but it's actually not, it's not there yet. Precautionary measures to avoid drying shrinkage cracking and crazing. Well, the next slides are going to show the graphs, but evaporation of bleed water, if it is 0.2 pounds per square foot or more, then we should use windscreens and fogging. If the evaporation of bleed water is 0.05, which is pretty low or more for silica fume and metakaolin mixtures, then you need to use windscreen and fogging. Or use evaporative retarders and curing. One thing that we have seen, and one of the recommendations from our side is actually with the blended cements, the 1L, some of the 1Ts, to go actually down to 0.1 or even 0.05 to avoid plastic shrinkage cracking. So the 0.2 is really meant for cement, for concrete mixtures with normal type 1-2 cement. Again, for 1L, 1Ts, it is actually better to go for a 0.1, better a 0.05. It's a little bit more on the contractor side, but that's how we can avoid, not avoid, but minimize drying shrinkage cracking and crazing. Should help there. Again, this is the graph. I'm going to go the next slide through it. For normal concrete, 0.2 per square foot per hour or higher, we expect issues. If concrete has silica fume or metakaolin at 0.05, we expect issues. Again, 1Ls, 1Ts, 0.1, maybe a 0.05 would be advisable. Doesn't want to work. Okay, here we go for an example. Let's go for an example. Like in the morning, air temperature 65 degrees. So you go up there and then you know what the relative humidity is, around 40 degrees. You go across your concrete temperatures, 60 degrees. Now you go down and what is expected wind velocity is a 20. Go back to the graph again and you see about a 0.13 pounds water per square foot per hour evaporation rate expected. If you do the same concrete mix, but now it's afternoon, mid-afternoon, you are at 80 degrees air temperature, relative humidity is still the same, but your concrete temperature has increased by 10 degrees, your aggregates got a little bit sunshine, so you are over, we are, give me a sec there, with 70 degrees concrete, we go down, wind has increased a little bit to 25, now you're already at 0.2 pounds per square foot per hour. So that means for an ordinary Portland cement, if it were a 1-2 in the morning, you still would be okay. There's less risk of plastic shrinkage cracking, but in the afternoon, there's for sure a higher risk of plastic shrinkage cracking and crazing. If it were a 1L, a 1T, I think I would already in both cases be careful and start fogging, curing beforehand to avoid plastic shrinkage cracking. So again, this is this graph is also in this in the PCA book. I took that literally from the book. Very handy, and there instruments out there at the construction site that give you the relative humidity, the wind velocity, and the normal air temperature. So you have all three, you know, the concrete temperature, and you can plot it in and go from there. Precautions to minimize plastic shrinkage, crack, and crazing. Fog the slab immediately after placing and before finishing. Just make sure that there's no water accumulation on the surface, or protect the concrete with temporary coverings, plastic sheeting, wet burlap. The thing with plastic sheeting might be that you're going to see some streaks, but what we see generally here, especially in Colorado Springs, they do a lot of the gutters and the curbs right now, and they're mostly protected with plastic sheeting. Trial mixes. This is directly from ACI 301. If you do a trial mix, the slump should be within 3/4 inches of the max specified. If it's an air-entrained concrete, the air should be within 0.5% of the required air content. There's a table in the annex. And the temperature of the freshly mixed concrete should be within 10 F of the intended max temperature as mixed and delivered. So here we already see an issue, because many of the mixed designs are done in winter in a nicely cooled lab, 60 to 70 F. So you get really good strength. I've seen that several times. And then we have an issue in the heat of the summer. In July, temperature is in the 90s. So you are really above the 10 degrees that it was done for the test mixture, and we're going to see lower strength. So that's something to consider when we do test mixtures in the lab. Do you want to click on the annex?
Oh, yes.
Just we can go back afterwards. Yeah. So this just shows the air content for different classes of F2 and F3 and F1, and what the nominal aggregate size is. If you have a nominal aggregate size, sorry, and then the class where your air content should be about. Sure. Yeah, so SCMs, supplementary cementitious materials, they're generally beneficial, what we already saw for the strength development. Generally, silica fume, metakaolin, they do not really impact the temperature of concrete because of their low dosage. They're generally dosed up to 10% of the cement, total cement content. But what we mentioned before, bleeding rates can be very slow for these mixtures and cause shrinkage, crack, and crazing. Aggregates, if they're hot, they have a really big effect on the fresh concrete temperature, since they make up about 70-75% of total concrete volume. So aggregates are by far the largest contributor to increased temperatures in the ready mix. That's something we need to consider. Chemical admixtures. Something we suggest is to use a hydration stabilizer or extended set admixtures that can be beneficial for hot weather. Water reducing admixtures, they help reduce the water cement ratio. So you're gonna use less cement and you reduce the heat of hydration, you reduce the total temperature in the concrete. Also something that we suggest to reduce the slump loss is to use a hydration stabilizer retarder just for the duration of the transport. Like if you are here in Springs and you have to go up to Woodland Park, you already know you're going to be 45 minutes on the road. Why not add a hydration stabilizer that will stabilize the mix for the next 45, potentially 60 minutes? That's how you can reduce some of the slump loss. And what we mentioned before, air entrainments are increased for hot weather, for hot concrete. So that's something that needs to be considered. Chemical admixtures, evaporation reducers. Evaporation reducers or retarders, they're typically sprayed on the surface right after screeding, bull floating, troweling, or straight edging. One thing that highly recommended is really follow the manufacturer's recommendations, waiting for dispersion before the next finishing process. These evaporation retarders generally contain a lot of water. So now, like, I just read one like Comfill, it says add 90% water to Comfill, to the concentrate that you get. So that means there's a lot of water getting on your surface, and please do not work that retarder into the surface. The evaporation retardant into the surface, because you work the water into the surface, you weaken, you increase the water cement ratio of your surface, and you weaken the surface. Depending on the conditions, you may have to reapply evaporation reducer. So that's just something to consider. Really helpful, but what I heard from several ready mix producers, they are quite often not correctly applied. So it really helps if the ready mix producer knows also how to apply them and make sure it's done correctly at the construction site. Here we have a few applications. Improper use of evaporation reducers, you already see that should be all nice and white on the left side. Completely inappropriate application, not enough. That this is a waste of the evaporation reducer. And on the right side, a little bit better, not perfect. And I think the truck is white because it's white, and the windshield is white because it reflects from the clouds. Don't think the truck was sprayed on, but
hopefully not.
I hope not. But again, it looks better, but I think it could be better done. And especially, why do you spray the surrounding concrete, the old concrete? Just spray the fresh concrete. Yeah. These are actual pictures here from the Denver area. Another one, and to be fair, I am not too familiar with them, but I picked that up from one of our larger ready-mix suppliers, is they suggest to use nano or colloidal silicas that are sprayed onto the surface during floating and troweling, meaning that these nanosilicas, they are worked into the surface. So they should not be applied afterwards and dried out. They need to be worked into the surface. Generally, these silicas help to improve the surface hardness because they chemically react with the cement hydration product. So at the very top surface, you get a harder surface. And what I heard is that, like in warehouse floors or so, that this is something that is quite often applied. Generally, nano colloidal silicas react faster than silica fume. And I heard that you should not use silica fume for these applications. It should be really nano or colloidal silicas for the surface hardening. Cooling of concrete materials. You know, we're in the midst of summer. We need to start cooling the concrete. A few examples here. If you want to reduce 1F the concrete, you can do that by lowering the cement temperature by about 8F. You can reduce the water temperature by 4 Fahrenheit, or you can cool your aggregates by 1.5 to 2 F.
Combine or either or?
Either or, either or, yes. The temperature of the cement or the SCMs generally has a minor effect because of its low specific heat and low and small amount in concrete mixtures. There's no specification for cement temperatures. Generally, specifiers and the DOTs, they limit the concrete temperatures and not the cement aggregate or water temperature. They only look at the concrete. And it is difficult. Once you have the cement on site, it is difficult to cool it down, further down. Aggregates. Aggregates, cool the aggregates by shading them from the sun, sprinkling them with water. One suggestion that we have is don't have your sprinkler on 24/7 on the ags. How about sprinkling them for 15 minutes on, 15 minutes off, 30 minutes on, off? It's really a trial. Why? Once you stop sprinkling your aggregate pile, the water starts evaporating from the aggregates. And evaporation is a change from liquid to vapor water, and this actually takes more heat out of the aggregate pile. One of the reasons, just why is a steam burn much worse than a water burn? It's because of the heat change from vaporization to the phase change. So just something to consider. If you need to sprinkle the aggregates, save some water, go to Home Depot or Lowe's, get a timer for your sprinkler and save some water. And likely get better cooling out of your pile. Mixing water should be stored in insulated mixing tanks, not exposed to direct sunlight. If they are, at least paint them in white. Same for the water pipes. Bury the water pipe, insulate them, shade them, or paint them white to keep, again, the water as cool as possible. And again, water has a very high heat factor, but again, because it's a pretty small amount, generally you can only decrease the temperature by about 8 F in the concrete mix. Ice is much more effective than water in lowering the temperature. One thing to consider, it must be completely melted once the concrete is discharged from the truck. Otherwise, you're going to have some pretty large voids in the concrete. Generally, the crushed ice must be stored so there are no lumps formed. What I've seen before is that you have like a big block of ice, and the ice is crushed or shaved right before it gets into the truck. Generally, the amount of ice should not exceed more than 75% of the total mixing water. And it's obvious that the ice must be included in the total water content. Generally, you can decrease up to 20 F if you start adding ice to the concrete. Dry ice, liquid nitrogen. I don't think we use that too often here in Colorado. I've seen actually liquid nitrogen being added to a concrete truck down in Dallas. It's pretty cool, but it's also pretty expensive.
I was going to ask the question in regards to the expense of liquid nitrogen as compared to something else.
I don't have the numbers there. I don't know, but I remember down there it was even 95 during the night, so they were actually at morning at 5 o'clock adding liquid nitrogen to the truck.
From the Southern States. Yeah. Dry ice is CO2.
CO2, yes.
This should have an impact, no?
The dry ice in this case, it's mainly just to cool down. Yeah. They're just directly injected in the central mixer. They can also be used to cool down the aggregates. One thing, if anybody ever wants to play with liquid nitrogen, dangerous to people. It's gonna freeze really fast, and it cracks your belts if it gets in direct contact with conveyor belts or metals, because don't remember, but I think the temperature like minus 180 C. Not sure how much that is in F, but it's really low temperature, so you have to be really careful. And again, very expensive to use. Calculation for cooling concrete materials. This is the calculation that's here out of the booklet. I'm not going to go into it. This is really up to the ready mix producer to do some of the calculations. And I just have an example here. An example as is cooled with water, cooled with ice. So if you have a zigzag mix, cement is at 150, coarse fine at 90 degrees. So we're in July. Water, 250 pounds at 75. If we just mix that together based on the calculation that we saw before, concrete temperature is going to end up around 93 F. High, too high. If we can reduce the water temperature from 75 to 40, we can lower the concrete temperature to about 85. If we now replace 125 pounds of the water, so that's about 50% replacement, with ice at 32, the concrete temperature can go down all the way to 68 Fahrenheit. So it's quite a big change. You see, you can go from 93 to 68. It is with some work, especially with the ice. Again, the ice must be shaved or crushed right before it goes into the truck. No lumps of ice should ever go into a truck. This is also from the PCA book. This shows, this is more for mass concrete. Generally, the rule of thumb is that the temperature inside the concrete compared to the surface should not differ more than 20 centigrade or 36 F. So in this example, we see by the heat of hydration how the temperature of the concrete goes up, and then it starts coming down after 2 to 3 days. We see that's the inside. The blue line shows the surface temperature a little bit lower, but if we remove the form, or we remove the, almost I would say, the insulation after 3 days, that temperature starts dropping faster than it's supposed to, and there's the potential that we're gonna get above the 36 F difference, and there we might have surface cracking. So it is really wise to keep the form in place so that the temperature remains higher, and that gradient, that difference temperature, it does not exceed 36 F. That's just something to consider. And there are some really nice temperatures, zones nowadays that you can place inside the concrete on the outside that show you the temperature, like maturity meters, and that gives you a good indication when you can remove the form before you get into issues of potential cracking, surface cracking.
Okay, I've found this on the web for good indication when you can remove the foam before. Check it out.
Sorry, my Siri was listening to me. Preparation before concrete in hot weather. There are some ACI guides. 305 guide to hot weather concreting recommends advanced planning when temperatures are between 75 and 100. 305.1 and 301 require that concrete as delivered does not exceed 95 unless it's differently specified. ASTM C94 states that difficulties may be encountered when you go above 90. And A1694, it does not set a max temperature unless the concrete is heated. So if the concrete is heated, it may not exceed 90 F. And this should be part of a pre-construction meeting, really important, especially in summer, how to make sure that the concrete that is delivered does not exceed the specified max temperature. This is from CDOT, directly from their website. The web link is underneath. It says hot weather limitations. Just going to read it. Placing of concrete during hot weather shall be limited by the temperature of the concrete at the time of placing. Mixed concrete that has a temperature of 90 or higher shall not be placed. Contractor shall provide fogging equipment and keep the concrete surface moist at all times. Fogging with an approved atomizing nozzle until the curing material is in place. And the aggregate stockpile shall be kept moist at all times. So that, again, that's directly taken from the CDOT spec. You can look it up, 60112B on page 19. So again, CDOT limits temperature to 90 degrees at all times. That's about it from my part. Well, are there any questions from the chat or?
There's no questions on the chat, and I just removed the restriction to unmute yourselves. So if you have questions through Zoom, please don't hesitate to unmute and ask the question. It sounds like we've got a question here in the room as well, though.
Yes, of course. Everything you presented shows that you lower the temperature at, let's say, 70 degree F. But how do you keep that? Because it seems to imply that that temperature can be kept quite long at a low temperature.
You mean the ambient temperature?
Yeah, I mean, you do all these things to lower the temperature, and then you have a graph showing at the lower temperature, the strength will keep improving. But this temperature cannot be kept low all the time.
No, it cannot. But
Well, the target is the time of placement.
So how long is just the placement is enough?
Yes.
Yes, that's the target, to get it lower at the time of placement.
And then
it's going to accelerate regardless.
Yeah. But one thing we have to consider, if it is mass concrete, because of the heat of hydration of the cement, we have to make sure that we don't exceed certain temperatures in the concrete. First of all, again, is that we maintain the 36 F or less difference between surface and center because of the cracking. And for precasters, it's really important that they generally remain below 158 because of delayed edge formation. So that is one of the things. But then we're going really to the board, but that's precasting, pre-stressing. It's different application. One thing that we know is like if for dams, for big foundations, windmill pedestals, generally engineers, they specify 25-35% pozzolan or fly ash just to maintain low heat of hydration, so we don't exceed the 158 for sure, but also that we have the temperature gradient between center and the outside doesn't exceed the 36.
So speaking of different applications, Nigel and Noah asked in the chat, do you have any experience using high early concrete mixes in hot weather? If so, can you talk about some of the practices you used to produce that mix and that met the strength requirements as well as met placeable and finishable processes?
Challenging me here from a. I'm gonna refer to Manny.
I was gonna say it's like if there's any producers that are online as well that want to jump in, please do.
One of the situations that we utilize is retarders, depending on the type of mix that you're going to use. You're not going to be able to. It's a high early, and you're adding heat to it. So it's going to take off hard. The only way to kind of control that is with a retarder, some type of retarder in there, keeping your concrete temperatures cool, like we discussed, lowering the temperature so it acts like a normal early setting concrete without having the additional heat causing it to take off even faster. Now, there's some stuff like a rapid cement that you might have to use some citric acid to slow it down. And we've had those applications in El Paso on the bridge to Juarez, going across the bridge, and they did a panel replacement on that bridge overnight in the summer. And they had to cut that out and place that in, and they used the retarder, the citric acid, just to get it set up and drive on it in 6 hours. So it's still a super fast setting without having the thermal cracking in there.
But
it was
it
using
gave them
retarders.
time for
Also
that
the same-
finishing time.
The same basic stuff that we do on everything else is cooling off your aggregates, everything we do in the summer to help bring that down, cooling off your aggregates. And using a chilled water, ice, whatever you can do to keep the concrete temperature at the point of placement down.
Thank you.
Thank
All right. Any other comments or questions? Robbie, it looks like you might have something.
Well, I was just gonna offer some advice on the high early and hot weather concrete from our experience as a producer. It's never fun to place or finish, but we have found is in warmer weather, we need to really dose high with water reducers and leave it a very high slump. So typically in warm weather, if I'm producing a high early mix, I'm leaving the plant at like a 10-inch slump and 12% air, anticipating 5 to 6 inches of slump loss in transit and a high level of air loss. So you start very wet with a very high air, and then by the time we get there and get it on the ground, it's going off. But that's about the only method we really found to overcome that, because we need that very rapid set to get that 4-hour strength. So you got to talk to the contractor about placement method, and they've got to be ready for a very high slump when it arrives, because it'll be a very low slump in about 30 minutes. So that's the number one trick that we've found to getting it placed in hot weather.
So I know we're going to talk about flatwork finishing next month, but Robbie, to that point there that you talked about of starting with a higher slump, I just want to reiterate and confirm you're talking about a higher slump, higher moisture, and but it's still within the water cement ratio requirements for that mix. We're not adding extra just to bring it back down on site, correct?
Yeah, no, we're using completely polycarboxylate based admixtures to get that slump, but we're just working very, very high to get that initial slump. And typically we're in the 3-6 water cement ratio range when we're in that high early strength criteria.
Yeah.
Thank you for that insight.
Nice.
Any other comments or questions? All right, well, thank you all for joining us. If you have any questions specific for Urs, his email contact is up there. If you have any feedback in regards to our Tech Tuesdays, please don't hesitate to reach out to me as well. And one last time to thank our sponsors. I missed a couple in our first initial presentation, but thank you to all 4 of them: Burnco, GCP, Wholesome, and GCC for all sponsoring these events going on for our Tech Tuesdays on a monthly basis. So hopefully we will get all of this information shared out fairly quickly with a PDF to everybody that was registered. A video link will be also offered out, and then we'll actually be posting this to YouTube for everybody to share amongst the entirety of the industry. So obviously these are more opinions than facts. So if you want to argue with them, please do reach out to myself or Urs. We like to fight about that. but please do take a chance to share this information with any of your clients. We are open for you guys to share this information. We hope to continue this information sharing in further months with the Tech Tuesdays. So thank you very much, and everybody have a wonderful day.
Thank you, everyone.